Hey everybody, thank you for attending today's webinar. As you can see today, we are going to be dealing with number properties, and as most of you know who have been using our curriculum, number properties is a very substantial topic. It's something that I think is probably one of the most important topics on the entire exam, given if you want to get a high quant score, anywhere from a 47 or higher. So, I'm going to start today. I'm going to do a little bit of divisibility. For those of you that were here at the last number property webinar, I did a lot on least common multiple and greatest common factor. So, we're going to start there. There is one thing I wanted to mention to everyone. For those of you that were here last week, I had mentioned a story about a student who used the Target Test Prep curriculum, and she had just gotten a 740 on her GMAT with a 49 on the quant. And she actually shared her story on Beat the GMAT. And, as I said last week, I know a lot of you are in the midst of the process, but if you need any sort of motivation, I think this story will give you a lot of hope if you are feeling like, you're at a place where you're not going to improve, or you can't improve, or can't get the score you want. The reality is that it doesn't get much lower than where this student was during her first test. So I definitely welcome all of you to read this story and, take a look at what she had to say. And, I'm sure you'll get a lot out of it. So with that said, I want to get into divisibility. So the first thing I want to do today is I actually want to talk about divisibility and how it actually can relate to least common multiples. So the first question here shouldn't be too bad for everyone, but I think one of the keys here is understanding how to translate this correctly, and if you do, it's going to make the rest of the problem a lot easier. So I'll give everyone 2 minutes as you start to get your answer. Paste it into the public chat box so everyone can see it, and from there we'll talk about the solution. Okay, so that was about 2 minutes. This is a great question because a lot of it, your success here is about how you interpret it. So there's 2 things we can do right off the bat. We know we're given that n is divisible by 15 and 24. So we could write it a couple ways if we wanted to write it mathematically. We could say n over 15 equals an integer and n over 24 equals an integer. Or we could say basically that n is a multiple of 15, because it really means the same thing, and n is a multiple of 24. The reason why the second version is kind of nicer is because now you're kind of forcing the idea that more than likely you're going to be dealing with least common multiple here. And the reason you know that is because we don't really know what n is. We're never going to know, but we've been given a question that says which of the following must, meaning in all circumstances, must divide into n here. So what that means is we need to find the smallest possible value that n can be with the given circumstances. And another thing that students sometimes struggle with is the idea of what it means to divide into. So essentially what we're saying is we need the answer choices to divide into n, and for that to end up being an integer. Now, we talked about least common multiple last time. 15 and 24 are not huge numbers, so you can always prime factorize it if you have to come up with the least common multiple. You see we have a 3 and a 5 here. We have a 2 to the 3 and a 3 to the 1 here. So if we're to take the largest of each one of our primes, we're going to take a 5, a 3, and a 2 to the third. And when we do that out, we get 120 as our least common multiple. So what we've determined is that the smallest possible value that n can be is 120. And now we go to our answer choices and we say which of the answer choices must, or Roman numerals rather, must in all circumstances divide into 120. We see right away that the answer is 60 and 120. So we see that the answer is 1 and 2, and it is B. So what I want to do next is I want to take this idea and expand it when we see data sufficiency. And you're going to notice that there are similarities that you can use, or if you'd like, there are other ways of dealing with this, which are actually fairly simple. So we will talk about that once I get it pasted up and everyone can go through it. But, generally, as Scott likes to say, you always want to make things as simple as possible. And so when a question is allowing you to do something in a fairly simple way, it's always a good idea to take that lead and not make it harder than it needs to be. So I'll give everyone another 2 minutes here and we can talk about this question. Okay, so that was another about 2 minutes again. Now, this question can be done in a number of ways, and what I really like about this question is without getting too technical with anything, you can determine what the answer is, and then I noticed most of you who put the answer basically put the correct one here, but we know x is a positive integer. We need to know if it's a multiple of 12. The first thing we're given is x is a multiple of 6. Now, one mistake that I see students make is they reverse multiple with factor. So factors of 6 are things like 1, 2, 3, 6. In fact, those are all of the positive factors of 6. Multiples of 6 are like 6, 12, 18, etc. So when we are going through statement 1, we can literally say, all right, well, what's the first positive multiple of 6? Well, it's simply 6. And then we just ask ourselves the question, instead of saying, is x a multiple of 12, we ask, well, is 6 a multiple of 12? And we can say right away, no, it's not. Then we move to the next highest multiple of 6, and we say, okay, x can be 12. Is 12 a multiple of 12? The answer is yes, it is. So then we move on and we say, okay, statement 1 is not sufficient. We do the same thing in statement 2. The first positive multiple of 18 is 18. Is 18 a multiple of 12? No. The next highest multiple of 18 is 36. Is 36 a multiple of 12? Yes. So we have another yes, no. Finally, we look at these two together and we say, okay, we know that x is a multiple of 6 and a multiple of 18. Well, what's really nice about that is that the values we used in statement 2 still fulfill statement 1, which says x is a multiple of 6. So we know right away the answer is E. Now, if that was somewhat difficult to see, you could have determined that the LCM of 6 and 18 is 18, but you didn't have to go there. Notice I didn't prime factorize. I really made this very easy on myself. Could have you prime factorized the 12, the 6, and the 18? Of course, but the reality is you didn't need to do that, and so it makes your life a lot easier when you're working with small numbers to keep the problem easy and simple, get your yes/no answer, and move on. And, it's going to allow you to do questions like this very quickly, well under 2 minutes, so that you can save your time, obviously, for questions that are a little bit harder. So I want to do one more similar version to this. This is actually a pretty challenging question, but it's a good one nonetheless. And there are actually a number of ways to deal with it, but we will go through kind of some of the different ways. So why don't we start this? I'll give everyone about 2 minutes again. Okay, so that was about 2 minutes there. And this is a very interesting problem because you're given a lot of information right off the bat that you can use to your advantage. And I actually want to go through two methods that work well in solving this question. And first one is really analyzing your given information and actually getting into some prime factorization and stuff like that. And the second one is going to be more of a least common multiple method between your statements and your given information. So we need to determine if m times n is a multiple of 120. Now, the first thing we know is that n over 18 is an integer, and m over 30 is an integer. And that means that n divided by 2 to the 1 times 3 to the 2 is an integer. And m, as in Mary, divided by 2 to the 1, 3 to the 1, 5 to the 1 is an integer. Now we need to determine if m times n over 120 is an integer. So that's the question. What's in green is given. So if we break down the 120, we're really trying to figure out, is m times n at a bare minimum divisible by 3 2s, a 3, and a 5. Well, what's really great about this is that our given information already tells us that we already know at a minimum it's divisible by 2 3s, so we know it's certainly divisible by 1 3. We see it's divisible by a 5, and we see that it's divisible by a 2. So what we can do is actually reduce this down to saying, well, is mn divisible by 2 to the 2, or is mn really divisible by 4? And what we did is we strategically used the given information to start eliminating certain factors because we already knew that m times n would be divisible by some of these things just from what we were given. So now we dive into our statements, and life should be pretty easy from this standpoint. Statement 1 tells us n is a multiple of 6. Now, what's great about statement 1 is if you notice in the given information, we're already told that n is a multiple of 18. Since 6 is a factor of 18, we know that any value n can be, like 18, 36, etc., is already going to be a multiple of 6. So statement 1, without putting any work in, it's just repeating information that we already know. So with that in mind, we can say right away statement 1 is insufficient. And that's great. And so what we did is we really front-loaded this question. We did a lot of stuff at the beginning, and it made it so that we didn't really have to put any work when we looked at statement 1 on its own. Statement 2 says m is a multiple of 12. Now let's go back to what I mentioned in the question where we simplified it out. We said, what do we really want to know at this point? And we need to know if m times n is divisible by 4. Well, if m is a multiple of 12, that means m can be things like 12, 24, 36, etc. Well, all of those are multiples of 4 because 12 is a multiple of 4. So we know that statement 2 is also enough information to answer the question. So statement 2 is sufficient, and the answer here is B.
Okay, great. Thanks, Jeff. Hey, guys. Good morning. Thanks again. Thanks so much for hanging out here with us. So what we're going to do in the next half of the webinar is we're going to look at some interesting questions that fall under the idea of properties of numbers. And just remember, the category number properties is really widespread and really varied, and it depends on how you're defining the category or property of numbers. So we're doing a really small sample today, but an important sample. Now, normally we don't talk strategy during these webinars, but we get more and more requests for a number of questions. So there's one I wanted to address with all you guys really quickly that seems obvious, but it seems to be the reoccurring theme. So, like you imagine a test of 19th century history, right, in the U.S. Well, or imagine, say, from 1800 to 1899. Well, if you knew the history really good from 1800 to 1850, you probably wouldn't take the test, right? Because you probably would know you can end up with a really low score, even though you know half of the history like the back of your hand, right? Well, it's funny, like we've all been through college and high school, then we get to the GMAT and we start doing weird stuff with our studies. Like we start trying to rush it and we start trying to cut corners and just get it done. And it's arguably the most important test many of us will ever take. So it seems so obvious, but I know a lot of you even here today are probably identifying with what I'm saying. Don't do that. Right? Don't do that. And what made me think of this was Jeff's story about, our most recent success story is that you can do anything on this test if you put in the time. But the converse of that is if you don't put in the time, you're almost guaranteed to get a bad score. And that's horrible. Then you're into retaking it, restudying it, and months go by and you miss deadlines. So the key, guys, is to make sure that you approach this test with full gusto, with excitement, and study for this test as you would study for a huge final exam, right? Don't do anything different because the best practices that would have worked for you in high school or in college are the best practices that are going to work today. And it sounds so obvious, right? It sounds like 2 plus 2 is 4. But yet so many students, right, they approach it. They're like, well, I know most of the math section. Well, you know what, guys? Knowing most of the math section quite often translates into a low score, because you're competing against peers who know all of the information on the math section, and they're driving that quantitative scale up into the high 40s and low 50s. So anyway, take that and think about it. Make sure you are preparing fully and properly. And when you do that, the test can be a walk in the park. It really can. So that's my little bit of obvious strategy for the day. Now, what we're going to do in terms of the content is we're going to do a number of questions that students typically have never seen before. And remember, guys, the motto is simplicity, right? We have ample opportunity to make things complex, but we're not going to. So let's start with this guy, and we'll do somewhere between 2 and 3 minutes, starting now. Okay, guys, a little bit over 2 minutes. So let's take a look at this. So keeping in mind that we're striving for simplicity. So we're looking for the number of zeros here. And these are usually called trailing zeros, right? So, for example, in the number 5,000, we have 3 trailing zeros. So trailing zeros are just these zeros that are at the far right of the number after the last non-zero digit. So basically we want to know, how many of these trailing zeros live in 5 to the 18th times 2 to the 20th. Well, it seems daunting, but it actually is really simple. So we have to ask ourselves, what creates a trailing zero? All right, so we're asking, what creates a trailing zero? Call them a TZ. What creates a trailing zero? Well, a long time ago, we learned that it's one simple thing. So, for example, in this number 5,000, or even easier, guys, let's take an even simpler number. Let's look at 50. In the number 50, where did that zero come from? Well, it came from a multiplication of 10, right? It's 5 times 10. It's the 10 that created that zero. Okay, so what is 10? Well, the prime factorization of 10 is equal to 5 times 2. So there we go. There you have it. That's what creates a trailing zero, right? It's the multiplication of a 5 and a 2. So with that, we say, I'm going to call this is just my terminology, a 5 by 2 pair. So each 5 by 2 pair is good for one trailing zero. So in other words, to get a trailing zero, you need to have one 5 by 2 pair. You can have a million 5s and no 2s and not have a trailing zero, or you could have a billion 2s and no 5s and not have a trailing zero. But if you have just one 2 and just one 5, you're going to get a trailing zero. Okay, so we can look back at the question. We're looking at, 5 to the 18th times 2 to the 20. So really the only question we're asking ourselves here, guys, is, well, how many 5 by 2 pairs are there? And you may have to scroll down, so I'm going to write down at the bottom of the screen in black. So we have 5 to the 18th times 2 to the 20. Well, this is 5 to the 18th times 2 to the 18th times 2 squared. And we can see that we have a grand total of 18 5 by 2 pairs. 18 5 by 2 pairs. So in other words, here there is an abundance of 5s. Excuse me, there's an abundance of 2s, right? Because there's 22s but 18 5s. So we can only connect 18 of the 5s with 18 of the 2s. So it's like, imagine being at a dance with 20 guys and 18 women. Well, you can only make 18 pairs of dancers, right? Same thing here. So those extra 2s don't have any 5 counterparts. So what this means is that we can create 18 trailing zeros. So if you looked at this number, it would just be one big number that had 18 trailing zeros. So the answer here is C. The answer here is C. Now, guys, I'm just curious. Would you do me a favor? Just put a 1 in the chat box if that's completely new to you. Put a 2 in the chat box if that's something you've seen before. Just I want to get an idea of type of problem, the difficulty level we should do next. Okay, cool. So some of you, it's the first time, and that's fine. And some of you, you've seen it before. It looks like some of you have seen it from our course. That's great. Okay, very good. Very good. So then let's increase the difficulty. And for those of you who this is your first time, we'll fully explain this problem so that it makes perfect sense to you. Okay, so let's try this. It's just an extension upon what we just did. I want you guys to, oh, let me see, that's going to be a little bit small. Let me start a new whiteboard. So the next problem we're going to do is a piggyback on the problem that we just did. Okay, there it is. Give that a whirl. Let's shoot for somewhere between 2 and 3 minutes, starting now. Okay, guys, let's give it a whirl. So this one is substantially more difficult, but still we can make it really simple. So the key here, we want to know how many digits are in this big number. And the trap here is to try and calculate it. So some of you may actually be able to do it. I mean, I don't know, some of you get pretty good multiplication. You may actually get it done in 4 minutes, and then you know what that means. You're in trouble now with problems down the line. So you never want to do that. You got to set a strict time for yourself on the test. Because if you spend 4 minutes on this question or a few others, you end up winning a few battles only to lose the war, and that's not the goal. So we've got to find a clever way of doing it. Well, the first thing we're going to do is let's find the number of trailing zeros that exist here, number of trailing zeros. And the way to do that is we're going to prime factorize this number. And in fact, guys, in almost all questions, you know, your best move is to prime factorize when you can, because prime factorization is a process that is shooting for simplicity, and that's always a goal. So 50 is 5 times 5 times 2, that's raised to the 8th. 8 is 2 cubed, and that's raised to the 3, and 11 is prime. So we'll just leave that 11 alone. We're not gonna do anything with him. Okay, so from there, what we can do is collect some of these terms. So this is 5 squared times 2 to the 8th. This is 2 to the 9th times 11 squared. Now remember, the 8 belongs to the 5 and the 2. So this is 5 to the 16th times 2 to the 17th, right, because it would be 2 to the 8th times 2 to the 9th times 11 squared. And now we're at a good place because we have the prime factorization of the number. Well, how many trailing zeros? Well, you can see that there are a maximum of 16 pairs that can be made, right? 16 pairs, right? Because it's 5 to the 16th times 2 to the 16th times 2 times 11 squared. So this right here gives us 16 trailing zeros. And then what's left? Well, it's 242, right? Because 11 squared is 121, so times 2 is 242. The thing you need to be careful of is we don't want to multiply these guys. We just want to realize, well, what is this number? Well, this number is simply 242 plus, I'm not going to use the comma there. It's 242 plus 16 trailing zeros, right? So 16 trailing zeros give you 16 digits. 242 gives you 3 digits. So this number has 19 total digits. 19 total digits. Okay? So again, sometimes it's hard to believe it can be that simple, but it is, right? And remember, the math in general is pretty straightforward once you kind of understand everything. Just do me a favor. On a scale of 1 to 10, 10 being like this makes like complete sense, 1 meaning this makes no sense, we just put a number rating in the chat box. 1 to 10, 10 meaning let's do like perfect sense, 1 meaning it makes no sense, and you can put anything in between. Okay, great. Thanks for doing that, guys. Okay, so we are going to make this a little bit more challenging here. Just playing around with this concept, and we're gonna give this guy a whirl here. And let's shoot for a little over 2 minutes starting now. Okay, guys, that's a little bit over 2 minutes. Let's give this a whirl. So this one's obviously substantially more challenging, but I'm going to actually probably show you 3 ways of doing this. So pay attention, because the first way is the worst way that would still, I guess, be acceptable, but in understanding the worst way, you're going to have a lot of theory here that's going to help. So 25 factorial, and excuse me for making you watch this, 25 factorial is the consecutive multiplication of all of these numbers, right? So you can see if I do this on the test, ahead of time is great because you get to learn some cool stuff. But if I do this on the test, not only am I wasting 8, 7, that's a 6, and see how easy it is to make a mistake, times 5, times 4, times 3, times 2, times 1. Okay, not only am I wasting time, but I'm wasting energy doing this. And it's easy to make a mistake when you're sort of trying to bang through a series of repetitive tasks like this if you're not careful. Well, what would I do? Well, the first thing I could do is say, well, I know every 5 by 2 creates a trailing 0, right? It's good for 1 trailing 0. I'm not going to do this because it's a long process. But what I would do is I would collect the number of 5s and 2s, right? So I'd say, okay, there's 1 5, there's 1 5, there, right? And I'd say, okay, there's 1 2, there's 2 2s, and I count them all up, and assuming I didn't make a mistake, which personally I probably would. And then I get the number of trailing zeros. I'd say, okay, how many 5 by 2 pairs could we make? And we'd have the answer. And that will work. And a lot of students couldn't even do that because they just don't know. They have no idea what creates a trailing 0. Like no one's ever taught them. Okay. So if you could do sort of what I just did, you would probably get it right. Now, let's tighten that up a bunch. Let's make you a bunch faster. So instead, guys, I want you to realize something. And this is uber important for divisibility too in general with factorials. So I want you to think about this. Are there going to be fewer 5s or fewer 2s in 25 factorial? And of course, there are going to be fewer 5s, right? So in other words, there's going to be excess 2s in 25 factorial, right? So in other words, there are going to be way more 2s, right? Let's kind of put it in common language. We'll say way more 2s, right, than 5s in 25 factorial. Way more 2s than 5s. So what does that mean? Well, if you've been paying attention, and you all seem to be doing really well with these questions, you know that you need to have a 5 by 2 pair to make a trailing 0, so you're going to be limited by the number of 5s that you have. So we're going to be held back in terms of making trailing zeros based on the number of 5s, right? So for example, if you had 5 squared times 2 to 1,000, for example, I'm not saying this is the right number for this problem, but for example, right, you're only going to make 2 trailing zeros. So once you realize that, the fastest thing to do, so this was approach number 1. It's okay. Approach number 2 is way better. We're going to say to ourselves, all we care about are the multiples of 5. Right, so I'll say 25 times 20 times 15 times 10 times 5. There's 2 5s in 25. There's 1 5 in 20. 1 5 there. 1 5 there. 1 5 there. And 1 5 there. So that's a total of 6 5s, and since we know that the 5 is a limiting factor, we can quickly see the answer must be 6. And that's really cool because that's a perfect example of how having a little bit of knowledge can allow you to make a really difficult problem really simple. Because I'd say this is a really hard problem, even though we're making it seem simple. But see, guys, if you just jump in and you try and do this problem because you see it on a forum or you see it in some book, you never really get the understanding you need to figure out why we can do what we just did. So it never actually sticks. And even if it does stick, you don't build the ability to apply it to future situations. Right? So you can see that by learning a little bit about trailing zeros and what causes them and truly understanding it, this is easy. Now, Let me show you the super fast. Well, 2 is super fast too, but let me show you a way that competes with 2 that has other applications that we'll probably get into in the next webinar. Well, we want to know the number of 5s in 25 factorial. All right, we just agreed that if we can determine the number of 5s in 25 factorial, we'll be able to determine the number of trailing zeros. Watch this. So how many 5s? That's what we're asking. Oh yeah, and by the way, guys, please make sure you fill out the feedback form. It helps us to make these webinars more meaningful and impactful for you all. Okay. How many 5s will watch this? Well, we're going to say, let's divide 25 by 5, and we see that that gives us just a value of 5. Well, now we're going to divide 25 by 5 squared, and that gives us a value of 1. Now, we're not going to do any more because 25 divided by 5 cubed does not produce an integer. Does not produce an integer. So what that means is there are 5 plus 1 or 6 5s in 25 factorial, just as we saw before. Okay. Now, guys, there's a couple caveats to this rule. I don't want to make you guys late for whatever it is you have to do next. So if you're using our course, you can find this in number properties. And for those of you who don't have the course, I will make sure I go over this next week again, just briefly, because there's a couple caveats here I want you to see that will help you to not make any mistakes with this little rule. So anyway, guys, I hope that was helpful for you. We look forward to seeing you all here, same place, same time next week. If you have any questions, reach out to Jeff or to me. And if you're not using our stuff and you like these questions and the solutions, we have about 3,000 more for you in the TTP Quant course, which is slowly becoming the de facto quant course for students to use. And anyway, have a great rest of your day, and we'll look forward to talking with you all soon.